Okay, welcome to video 2 of the ChipSeek day. What we're going to be talking about now is the model-based analysis of ChipSeek data, or a program called MAX, which does peak calling. So if you want to read up a little bit more about how MAX works, and once again, I got a lot of figures for this portion of the talk from this paper, I suggest going and looking at their most recent paper, which is identifying ChipSeek enrichment using MAX. So the general analysis pipeline to get through peak calling is going to start with your fast queue. So you get your fast queue from the sequencer, and the first thing you do is map. So what's really important here is whatever mapping tool that you use, be sure to map uniquely. This is really important when it comes to calling unique hits, especially because a lot of times chip can be sort of shorter and have some redundant parts of it. So you want to get rid of the redundancy and only do unique mapping. For bowtie 2, which is what you learned how to use earlier in this class, these are the settings that I use. So you do -q, which means a fast queue input file. I like to add the --Fred33, which indicates that you're using the Illumina quality score of Fred33. You don't have to put this in. It does default to Fred33, but in case of any, I always like to keep documentation for even the default stuff. -K1 means map the reads only once, only report one mapping per read, which is the uniqueness. And -P32, in this case, the P is for just the number of processors, so multi-threading obviously makes mapping and stuff go much faster. And then you must do a -X, which is your bowtie index file, which you learned how to make earlier in this class. The next thing you want to do is put in your input files. So if you have only one input file, so it's single end, you do a -U. However, if you're using paired end data, which is common a lot of times for ChipSeek as well, you have to map as paired end, so -1 and -2, and then give it your out file, which is your -S. So like I mentioned before, be sure you're using the correct method for the data that you have, whether it's paired end or single end. The data we're going to be looking at today and examples in class are all going to be single end. And be sure to use the same exact strategy for your inputs as well as your replicates. That way you can compare them when you do the peak calling. So after mapping, I like to go SAM to BAM so that I could visualize my files in IGV, as well as BAM files are much smaller than SAM files, so I like to make my BAM files and then get rid of my SAM files if I don't need them anymore, just because they're so much smaller. And you can always convert BAM back to SAM if you ever want that SAM file back. And so I use a tool called SAM Tools to do this. I believe you have probably covered this as well throughout the course when visualizing with IGV. So the next step is peak calling. So peak calling can take in both mapped files in SAM format or BAM format, but they do need to be mapped files. So this is the general overflow for the MAX program. You start with both treatment and control, and with both of these, you remove redundancy. So you remove any reads that are mapping at the same position, so that you're just getting basically unique reads from your fast queue. For your treatment section, the first thing it wants to do is determine areas of enrichment, and to do this, it selects 1,000 regions that have between 10 to 30 fold enrichment relative to the genome background. And what this is going to do is build a model, and to do that, in this model, it's determining a fragment size, and then it's going to shift all your reads towards the 3' end by that fragment size, and we'll go over a little bit later what that looks like. You then scale the two libraries together, call candidate peaks relative to the background. You calculate the dynamic lambda for the candidate peaks. We'll talk about that a little bit more, but that's basically adjusting the background per position to better calculate peaks. You will then calculate a p-value for your candidate peaks and determine the false discovery rate. So here I am showing example data that we looked at in the last slide, showing a peak in max. And I've colored this data by the direction that the read is mapping, and or on which strand the read is mapping. And so one thing you might see from here, I hope you can see from here, is that in your peaks you have reads in red and blue, and they seem to be on different sides of the peak. And so what this is saying to Max is because you have a peak and you're only sequencing one end of your piece of fragmented DNA, one end's going to come from one half of the peak, and one end's going to map to the other half of the peak or of the fragment region. So Max is going to build a model that's going to shift both the forward tags and the reverse tags into the center to make one single peak, and call that at the center of the peak. And this is what makes Max better than any other program that came before it, because it does this model building and shifts the peaks to the true center of where the factor is binding. So this is once again just reiterating the model building aspect that I just talked about. So given a specific sonication size or the bandwidth, which you can enter in yourself, a high confidence fold enrichment or M-fold, so there are default settings which is between 10 and 30. Max will then slide windows of 2 times the bandwidth across the genome to find regions where their tags are highly enriched. And so once this model is built, a D is estimated, and then all reads are shifted by D over 2, and so D would be the fragment length as it was estimated. You could also set this if it's unable to build a model, and so it shifts all the reads to the center over the overall peak, and then it uses a statistical test to determine which peaks are significant once everything has been moved to its center. And then a local captures local biases in the genome, and so there's local biases in mapping and those sorts of things. And so it's really important to have your input and in addition to help calculate, in addition to your regular chip sample, in order to help calculate and to reduce these local biases. Okay, so how do you run Max? You give it 2 input files. You give it your chip alignment file and you give it your input alignment file, and it's going to compare your chip against your input. There are variations where if you're trying to maybe look for differences in binding, you can give it 2 different chip files and it will compare between them. But for the purposes of this class, in the most traditional form, you give it your chip alignment file and your input alignment file. So this is already post mapping. It's going to give you several output files. It's going to give you a peak Excel file, and so this file is great because it lists all the peaks it found, the p-value for those peaks, the width of those peaks, where they're located, where their summit is. It's the most comprehensive file that they give. The next file that's going to be really important, the next 2 files that are really important for downstream analyses are the peaks.bed file and the summits.bed file. These are bed graphs, and so we'll look, or they're bed files, so we'll look in a moment what bed files look like, but they're just tab delimited files that give you location information. And so they just, for each line, give a location of a particular peak or a particular summit. There's another file called peaks.encodepeak, which gives a little bit more information than the regular bed file. It gives information about where the summit is located within the peak, as well as the p-value and q-value. And then it has this model.r, which is just, R is a mathematical program that Max uses, and that's just an output of the model. It's not necessarily important for your downstream analysis, but Max uses this folder to continue on with your analysis. Okay, so Max has several different input parameters. The ones that are going to be most important for us today, most things can otherwise be run on default, but the most important ones are your input file type. So in this case, whether you're using a SAM or a BAM, you need to specify the input file. It will do the detection on its own, but I always find it's better to annotate for yourself what you're putting into it. Effective genome size, so -G. This is really important because it's going to help with statistics depending on the size of your genome might affect how often you see a peak or how unique that peak is, and that sort of thing. You can also set the p-value and q-value threshold, so it'll only report peaks that pass this threshold. And the other thing you can set, which will help with the model building, is your bandwidth. So this should be the your fragment size that you amplified, or has to do with your library prep. One additional parameter is important for broad peaks, since doing this dash broad. And what this will do, the program tries to merge close peaks together. If you tell it that it should actually be a broader peak, it'll merge nearby calls together. Okay, so let's go ahead and try and use max. Okay, so I am going to show you how to use max in the terminal. So the first thing you need to do is load the max module. So module load max, and I just tab completed there to go ahead and let it fill in. So now that's loaded up. So now I can type in max2-h and get this help screen. So let's walk through this really quickly. I'm just going to scroll up to the top. This is going to go over the usage on how to use it. So it's max, and then you get a -t file, which is your T file, which is your treatment file, -c, which is your control file, -f, which is format. So you can give it, you can say bowtie, SAM, BAM, ELAND is another format, bed, or you can just let it run on auto and figure out what type it is. I like to go ahead and annotate that, because when I keep like a digital lab notebook, that way I could go in and see what settings I used. It says the next required setting is this -g, which is the genome size, as I mentioned before. What I didn't mention is there are actually some presets in here for human, mouse. So for human, you just do -g space HS. For mouse, you do MM for musculus or whatever. In our case, I did a custom genome size because I only looked at chromosome 21. So I inputted that custom genome size into the -g. What else? It says -n. We can scroll down here, which is one of the other required ones. I didn't miss it. N, name, experiment name. So when you give it this name, it will output a file. It will output all the files with this name in the front of it. So if you gave it CTCF input, or just CTCF max, it would add CTCF max and then whatever file name it wanted to, so like peaks.bed or summits.bed after that name. Some other settings you can play with are, I mentioned before, this bandwidth. So you can set your the value to use in the shifting model. You can also custom set the Q values and the P values. I set a Q value, and it's actually the same as the default. Once again, I do this to keep an annotation. mfold is the amount of enrichment it uses to build the model. I like to just go ahead and keep that at default. Some other settings, you can change how big your lambda is, whether you want it small or large. So lambda is this setting that calculates local background, and so normally it's somewhere between 1,000 and 10,000 base pairs is that normal background, and you can set that with these settings. If you can't, sometimes unfortunately you can't find a model, so you can't build that model, and so in that case you can just go ahead and say no model, and then tell it a shift size to automatically shift your reads by, which should be about half of your fragment size. And so you can also keep duplicates or downsample or scale differently. So right now it scales the large sample to the small sample. In this case, you can scale the small sample to the bigger sample. And then the other important setting we talk about, you can read through the rest of these on your own and play with these settings as you want, but the other one that we talk about is this broad setting. And so when you're doing something with broad peaks, you use this setting, and it will try and call broad peaks by linking nearby highly enriched regions together. Okay, so now I'm going to pull up my script that I used to run this. So let's just do less, and this is my max ctcf.pbs. And so let's just go through what I used, how I submitted this first. I want to point out, first of all, this is a very important setting, this pbs-v. When we did the load module there, we loaded in the max module. That module is important because max has some dependencies, and so we've made a model on VIKEys, or a module on VIKEys that takes care of these dependencies. So once you load that module in, this -v says, okay, there's a module loaded, run that module for this script. And so, okay, so each of these, I want to point out, if you haven't seen this notation before, this is all considered one line. I've done this backslash to indicate I'm going to move my writing down onto another line, but it's still all considered as part of the same actual line. And I just do this to make it easy to make adjustments to the settings. So I gave it its treatment file and the control file, which in this case are both BAM, so I went ahead and told it that I gave it a BAM file. I set the genome size, which is 46 million, which is the size of chromosome 21, and I set the Q value. This is default, but I like to annotate this anyway, so I can always go back and know what my settings were. And then I gave it the name of the file I want it to go to. What you can also do is I've made a new folder with this max out, and so I want it to go specifically into that max out folder and not clutter the folder that I'm in. Okay, so let's go into that max out folder and see what's in there. Okay, so we have several files here. As I mentioned before, you have this R model, which is more of an internal file that you really don't have to pay attention to. There's this peaks.bed. So let's look at this bed file and see what it looks like. Okay, so this is what a bed file looks like. It's a file with location and names in it. So all of these peaks occur on chromosome 21. It gives you the start of the peak, the end of the peak, the name of the peak, and then the score for that peak. And you can go through and you can see that there's lots of different peaks. One thing you could do, if you were savvy and learned how to write a couple of quick scripts, which I highly encourage that you do, you could use something like Python or Perl to parse this file for only scores above something, and then you could go scores above 200 and go look particularly at those scores. The summits file is really similar to that. So instead of peaks, we put in summits. It's basically the same layout, except for this is giving the location of the summit of that peak. And so as you can see, if you look here, this is literally just one base pair. It starts at 38 and ends at 39. So it's just giving you the one base pair summit. Okay. So what else? There's an Excel file here. This is probably the most useful file, as I mentioned before, because it's going to give you your p-value, the name of your peak, the location of your peak. It's going to basically give you all the information that you need to go with it. All right, so what can you do with some of these files? The first thing I do once I run max is I go ahead and pull up IGV, and I look at these I look at my sequencing files as well as this peaks bed file in IGV. So I'm going to go ahead and pull that up. Okay, and if I zoom, I can. So this I'm looking at chromosome 21, which is where we did where we looked at. We sampled from reads just on chromosome 21. If I click this CTCF chromosome 21 peaks.bed, I can hit Control F and skip forward to somewhere where there's a feature in this file. So it's just going to go ahead and skip me forward so I can see one of these peaks. And so here it's calling a peak. This is Great, we see nice enrichment over this region. We can actually mouse over this peak and see that it has a score of 121. We don't see hardly anything from the background there, so that's good. And I can just click Control F and jump through a couple of these. And this is basically what I like to do. If I know a place where this transcription factor is supposed to bind, or that other people have reported a binding, that's another great thing you can do. You can up here type in that gene name or that location and jump right to that and see if in fact you are seeing binding there. Okay, and so sometimes you might see like this peak isn't as good as that last one, and you mouse over it, its score is much lower. It's a 7 rather than like 120. So that's good. So the data looks nice. It looks specific, and there's not too much background. So I think that that's a really good sign. So I mentioned that broad setting before, and so I just want to show what some IGV data looks like from that broad setting. So here, in this case, I'm doing pole 2, which is mixed with should have peaks and broad. And if I zoom in so that I can see peaks, and then I'm going to go ahead once again and click on this pole 2 and do Control F, and it's going to bring me to somewhere it has a peak annotated. So I do see a little bit of a peak there, and if I keep clicking through, I do see some slight enrichment. And it's not as strong as the sharp chip is, or the CTF that we were just looking at was. That's probably because they don't have enough actual reads to do something as broad as pole 2, and so that comes in planning your experiments properly. So here is an example of a peak that it has several peaks called in this region. This is in a gene. I would expect pole 2 to be working here, so I would expect pole 2 chip to be located here. And you can see it's calling several peaks when this is probably just one broad peak. And even though we use the broad setting, or I use the broad setting on this, I'm still getting several peaks. And so that's one thing I wanted to address back here in PowerPoint is peak calling on broad source data is very different than peak calling on point data. So here we have point data and then we have broad. So how do you call a peak when it's so broad? And the fact is, Max is really bad at it. It has a really hard time. Algorithms that use HMMs are generally a lot better at doing this. And this Chrome HMM is one that ENCODE suggests using. I'm not going to go over how to do this at all today in class, mostly because of time problems, and what I'm most familiar with is using Max, and I haven't used this Chrome HMM. But I hope what we have done for you is given you the tools you need to go and use these other programs on your own, and that you can confidently do that. Because it's really just reading the help manuals. You know how to run programs now, so you should just go forth and do it.